spectroscopy. So just I suppose just take a pause for a moment. This lecture itself is going to be a little bit shorter than some of our previous ones because there's some additional resources and activities that I'd like you to have a look at. Our spectroscopy is a little bit different than our UV and our fluorimetry because this time, in addition to looking at the theory behind it and the instrumentation, we also have interpretation of our spectra. And that's a skill in and of itself. So it's something that I want you to familiarise yourself with this week, but we will also be looking at it in the lab next week. So it'll be a nice introduction now just to kind of to begin with really. So we're going to begin with the principle of IR spectroscopy. So we're still using our electromagnetic radiation, so we're still using that, that spectrum that we would have talked about previously with our UV and our fluorimetry. But this time we're looking at wavelengths between 400 and 4000. And all that's happening here is electromagnetic radiation between 400 and 4000 is being passed through a sample of interest. This sample can be a solid, a liquid or a gas. And the radiation is being absorbed by the bonds within that molecule within the sample. And this radiation causes these bonds to either stretch or to bend. And the wavelength at which that radiation is absorbed is characteristic to the bond absorbing it. And when I'm talking about the bond, I'm talking about the functional group there. Whatever radiation is not absorbed by that bond or by that functional group is transmitted, okay, so it's passed through the sample. And this gives rise to an IR spectrum. And an IR spectrum is going to have your transmittance, okay, so if you want to think of it as your electromagnetic radiation transmitted through the sample against a wave number. And what happens is we end up with a spectrum like this, okay? So it is like a graph, okay? So on our x-axis we have the wave number and on our y-axis we have transmittance. And transmittance is being measured in percentage. So what I want you to notice this time is unlike our fluorimetry and our UV spec, where our baseline is usually down the bottom, for IR our baseline is actually on the top, okay? So we'll start to look at that a little bit later. So again, this is transmittance. So if you have something with high transmittance, it means it wasn't absorbed by the sample. Okay, so if you have 100% transmittance, that is equal to 0% absorbance. So if you have something that absorbs a lot, okay, so we have high absorption intensity, that means we're going to have low transmittance, okay? So any bonds that are present there, and quite a substantial amount, we're going to see them reaching all the way down to the 0 here, okay? So we're going to see 0% transmittance, or, lower amount of transmittance. And if it's not absorbed at all, i.e. those bonds aren't present, they're going to be up at 100% transmittance. So just to keep that in mind. What we're also going to start to see is that we have various different regions for various different types of functional groups or bonds. So, and these are just a few of them, okay? So I have provided you with a table on Moodle for basically every single type of bond. And this will help you to interpret some exercises and some example IR spec later on. But this kind of region here, so if we say from 3000 upwards, common things we're going to see are OH stretches, okay? So OH going from alcohols and coming from carboxylic acids. So typically in an alcohol, we're going to see this broad U shape, and it's going to be typically relatively intense, okay? So possibly anywhere from 50% and down transmittance. We also start to see amine groups here, okay? So primary, secondary and tertiary amines. And again, they will be referred to in your table, so you can take your time kind of walking through those. But we'll see those appearing around 3,300, 3,500. We also start to see lots of carbons and hydrogens in this region here. So if we're looking at anything like alkanes, so just long chains of carbons and hydrogens, we'll typically just see a peak up around here, okay, up around the 300 mark, or 3,000 mark, sorry. There is a region for triple bonds. We don't really, not that we don't encounter them that much, but typically it's not a functional group that we're really looking for, because again, when you're using IR spec, you may be using it for determination of, say, reaction progression, or is it a product that you're looking for. And triple bond may not be a functional group of interest. Something like an OH definitely is relevant. Amine groups are relevant, and these kind of groups, okay, so C double bond O is something that we look out for quite a bit. So, and unlike our OH stretch, which we said is going to be broad and round, this is going to be long and sharp. So this is going to appear around 1650 to 1800. So this is going to be in our carboxylic acids, it's going to be in our ketones, it's going to be in our aldehydes. And then one that isn't actually mentioned here but is worth noting, so down around 1100 we'll see something kind of similar. So maybe not as intense but definitely as sharp, which is going to be a C single bond O at around 1100. So again, that may be in our alcohols and it may be in something like our ethers and our esters. We also have something known as the fingerprint region. And overall, this region isn't really helpful. There still are certain parts of it that may help in figuring out what a compound is. So here you're being told around 680 to 860. You might be able to figure out if something's ortho, meta, or para. So this is on your benzene rings, okay, so your substitution patterns on your benzene rings. It can also help determine if you're conjugating metals, okay, coordinating metals to certain groups. It can also help in that regard. But overall, it's too complex. There's too much going on. So typically, not very useful. There are some that suggest that you can use the fingerprint region to compare the product that you've made within the lab to a reference sample. But overall, you'd still look at the entire spectrum. You'd still want to work through and see what peaks should the molecule have. So what functional groups are within the molecule. And then begin to work through, are they present in the spectrum or not. So we're going to just kind of walk our way through some of the theory. So what actually causes these peaks to appear. And we're going to have a look at some of the instrumentation in this lecture. So, as I said, we're still on the spectrum. We've now moved on from our UV and our visible light, and we're now in the infrared spectrum. And just as these were divided up, this is also divided. So we can have our near infrared, which is between 200 and 10. We can have our mid-infrared between 4,200 or 4,400 for most of your instruments. It won't typically go as low as 200. And we have our far infrared. For anything that we're doing at the moment, it's going to be mid-infrared, and the instruments we use will focus on mid-infrared as well. So what actually causes this? So we've already said that electromagnetic radiation is passed through a sample, causes certain bonds to vibrate. In order for those bonds to vibrate and to interact with that electrical component, it must have a dipole. We're going to use hydrochloric acid or hydrogen chloride as an example here. So when we talk about dipole, it's a difference in charge within the molecule. So, and what do I mean by charge? So there's something called electronegativity. And there's some atoms that are more electronegative than others. And you can use tables for this. So I'll include a table on Moodle just so we can compare. So there's certain molecules that are highly electronegative. So these are going to be some of your halogens, so chlorine, fluorine, bromine, iodine, and other atoms like oxygen and nitrogen. They will all be very electronegative. And what that means is they're greedier. They pull electrons towards themselves. Okay, so if you think this is a bond here, and there's electrons obviously in amongst here, the chlorine is going to pull those electrons closer to itself. Electrons being negatively charged are going to cause this region of this molecule to be more negatively charged. And we indicate that with this symbol, okay? So delta negative indicating a slightly negative charge here. Because hydrogen has had its electrons pulled, not necessarily fully away from it, but further away from it, it now has a slightly positive charge. So delta positive, and this forms our dipole. Okay, so difference in charge between the two. And that dipole is required to cause, that dipole is required for the electromagnetic radiation to actually interact with the molecule. So if we have a symmetrical molecule, so something without a dipole, so this is going to be something like a nitrogen, so just nitrogen gas, oxygen gas, okay, they're not going to absorb infrared radiation. But that's not really a major issue because most of our organic molecules have some degree of asymmetry. And we know that most of our organic molecules are not only two atoms, don't only consist of two atoms, they become far more complex. So there's definitely something to work with, and there's definitely an IR spectrum for them. And within each bond, there is numerous ways for those bonds to vibrate. And we have examples of them here. So we're going to have 3 different ways. So we're going to have stretching, we're going to have bending in plane. Okay, so we think that in plane just means on a flat kind of surface, and bending out of plane. Okay, so again, kind of taking up a 3D space. And we can have that as a symmetrical, or we have it asymmetrical. So we can look at some of these now. So symmetrical stretching. If we think, okay, so this is our central atom here, okay, so just our grey sphere here is our central atom, and then we have a red and a blue outer atoms. And when we talk about symmetrical stretching, it literally just means that these bonds in between them are pulling away at the same distance and at the same time, so symmetrically moving away and towards the centre. Symmetrical bending, okay, so these arms are just bending up and down at the same time. So this can also be known as scissoring. We can have symmetrical bending out of plane. So again, still kind of moving in the same direction, but now just in a 3D space, and this can be known as twisting. We can have asymmetrical movement. So the same thing, so stretching, bending in plane and bending out of plane, but this time asymmetrical. So this time, instead of both atoms moving out and in at the same time, they're just moving out and in at different times. So this, as this red outer atom moves in towards the central atom, this blue one moves out. Okay, and they just move in and out asymmetrically. We then have bending in plane. So as one goes up, one goes down. And then we have our asymmetrical bending or wagging. So again, this time they're just twisting in, or they're wagging this time, okay? So, yes, wagging asymmetrically then. And these all give rise to different absorption bands or peaks within our IR spectrum. Now, each of these may be possible for 1 or 2 particular types of bonds. And obviously, as we get more and more complex structures, that means we have more and more complex IR spectra. So we can get loads of data from an IR spectrum. And this is just to show you, I suppose, in real time what could be happening. Okay, so we have carbon dioxide, which is CO2, so carbon with 2 double bond oxygens. So again, we have our symmetrical stretching, so both going out and in within the same time at the same pace. We have asymmetrical stretching, so as one moves into the central atom, the other one moves out. We have bending and we have wagging. We already said when we looked at our IR spectrum at the very beginning that we have different intensities. Okay, so some transmit fully. Okay, so nothing was absorbed, so they have 100% transmission, which is up at our baseline. Okay, it's up at the top of the spectrum, so therefore nothing was absorbed. But when we have 0% transmission, or a lower percentage transmission, that means we have a higher rate or higher intensity of absorption. And this is typically when we're going to see those lovely big sharp bands, or big broad bands. And this intensity that a bond can absorb radiation is dependent on its dipole moment. So we have a couple of groups here. Okay, so a carbon bound to an oxygen, carbon bound to chlorine, a carbon bound to nitrogen, so on and so on. So your carbon oxygen is going to be more electronegative than, or has a greater dipole and greater intensity than a carbon to chlorine, than a carbon to nitrogen, and so on and so forth. This is the same here when we're looking at, say, simpler, or not simpler groups, but more polar groups. So an oxygen bound to a hydrogen is greater and it's going to have a more intense band than a nitrogen bound to a hydrogen or an amine group. So our hydroxyl group or amine group, and then our just a plain old CH group. So this and that just stands to practice, okay? Because typically when we see an absorption band or a peak corresponding to OH from an alcohol or an acid, they're going to be intense. They're going to be one of the most intense bands that we find. And it's definitely going to be more intense than NH or an amine group. And both of these are most certainly going to be more intense than plain old carbon-hydrogen bond. And this is related to Hooke's law. Okay, so you may have heard this, you might get a flashback to junior cert maybe. So this is all related to your vibrating spring system, okay? So when we're talking about bonds within IOR, they can be compared to a very physical model of a vibrating spring system. And our Hooke's law basically states that the vibrational frequency is equal to the strength of the spring. So the stronger the spring, the higher the frequency. You can also say that vibrational frequency is inversely, okay, so inversely proportional to the masses at the end of each spring. So the lighter the weight, the higher the frequency. So how does that apply to IOR? Well, the springs are your bonds, okay? So stronger bonds are going to absorb at higher frequencies. So therefore weaker bonds are going to absorb at lower frequencies. Bonds between lighter atoms absorb at higher frequencies, and bonds between heavier atoms absorb at lower frequencies. And this can help you predict where certain bonds and certain functional groups may appear on your spectrum. Okay, it's not used as much anymore because obviously a lot of this is now is computational. Okay, but it's just worth being aware of it. Okay, so the relationship between IR spectroscopy and Hooke's law.